So, me again. I haven't really prepared a presentation, so this is more that I'm going to show you some proof of concept implementation that we have been working on. And I'm having a couple of students that are going to continue working on this during the summer. And the background is that we have been using a simulator for microprocessors in a computer engineering course or a microcomputer engineering course that we give to students at the D program, computer science program. And when learning how to program in assembly language, it's useful to be able to see the inside of the processor, what is actually happening inside the processor when you're running the assembly instructions. And to do so, we implemented a simulator in Java, and that was around 2004, something like that. So it has been around for 20 years. And we have had many students working on this during the time and improving the user interface and the models shown and so forth. But it starts to show its age, and I have no particular interest in continuing working with Java source code. It was a long time since I programmed Java, and I would probably not understand what we did early on. And we wanted to see if we could redo this in Rust. And one of the things here is that Rust is good at many things, but perhaps not most known for GUIs, for graphical user interfaces. But over the last few years, still there has been quite a lot of development going on. And one of these frameworks, I will show you a bit on the background here. I can make it like this, I think. Should be possible. No. Open preview, that was what I was trying to do. So I'm not sure if it's too small. Should I make it a bit larger for you to read?
It's fine.
Yeah, you can read. So maybe you read it to me. No, just kidding. I'm really into a lot of things. Rust programming is one thing, and also I'm into computer-based music and synthesizers and stuff like that. And to program virtual instruments, there is a standard by Steinberg called VST. Some might know it from other, yeah, we have some musicians here. And it's quite horrible. And I'm probably not the only one that has this feeling. And programming like these applications for a DAW. A DAW is a digital audio workstation. That's a program that runs these virtual synthesizers and so forth, or effects. It could be anything. So there are some limitations into how you write the graphical user interfaces. So I was interested in experimenting with this and Rust, and then I ran into the VCI framework, and that has the ability to integrate with these DAWs. And I did some early experiments, but nothing really finished, so it's ongoing work. But at least I got an interest in the VCA framework. At that point, I think it was named something else, but now it's VCA. So I think we can bring it up here. It should be clickable links. This is the VCA framework in any case. And now I have to find my way back through the hundreds of windows that I have open. in any case, the community around this VCA framework is great, and Geometric, the guy that designs it, is super helpful, and we have had some discussions whether this type of application would actually be possible to implement using VCA. And so he has been very supportive, and there are others as well that has helped me with questions that I ran into. And I'm no graphic programmer, so this was also new to me, and I'm no GUI expert at all. So it was just an interest to see whether we could replicate what we already had in Java using Rust. And in Java, you have this dynamic memory, and you have garbage collection, which makes it easy to handle data. We don't have this strict sharing sort of enforced on us and so forth. So it's a bit easier to distribute data in a system than it's using Rust. So I was facing a lot of issues trying to find a structure, how to do this, because we wanted some key properties for this. I can show you this. This SyncRim was the Java implementation, and we call this SyncRim because now it's the Rust implementation. But it's the same program, or should do a similar thing at least. So it should have, for the components describing the processor, it should have a set of pre-made components that every processor is using. For those of you who are into HDL design, you know that we always have some registers, we always have some adders, we have some multiplexers, and so forth. So these commodity components should be there. But it should also be easy to extend so that you could add new components. So that was the idea, that you should have a library of predefined components and extendable library. And then it should be possible to alter models written using these components. And models would be like a description of a processor. But it's not restricted to simulating the way the processor works, but in general, any synchronous logic circuit. But at the level, when you're doing HDL design, that is designing real hardware or running onto an FPGA or simulating, you're usually simulating it with waveforms. And waveforms are just values or zeros and ones. It's very hard to interpret. So writing a program and figuring out if the program does what it's intended to do by just looking at waveforms, that's not really going to cut it. You want to show results in terms of what is the value of this register in a structured way. So you can see that we have the register file where we have our registers, we have the data memory, we have the instruction memory, and so forth. So these components should be visible in the simulator, not waveforms. So that was the design goals, and the technologies used was then VCA as the framework. So it's a Rust-based development from the ground up. So there is very little or any other code than Rust in it. And it has very good ergonomics. It's a deferred rendering or deferred mode rendering framework, a declarative framework. It's cross-platform, so you can run these applications on Linux, on Windows, on OS X, and so forth. Here also, this VASM is possible, so you can run it in the browser as well. And yeah, modern and declarative, and you can have it scaling, so it works with high DPI screens as well. and it has CSS-based theming. So instead of annotating each component with attributes, you can just tell it to belong to a class, and then you have a CSS defining the properties of the class, coloring or size or something like that. And as I mentioned, it's a great community around this. And another thing that we are using is Serde, and most of you have probably run into Serde at some point. And the trick here is that we would like to store models with different types of components in it. And you can't really do that in a simple way without erasing the type. And we use a trait object in order to define the commonalities of a component. And then we use a technology called type tag that actually emulates, or what it does is that it generates an enum under the hood for all possible variants. So that means that it's possible to treat trait objects as one also for serialization and deserialization. And then for the execution or simulation of the model, we are using petgraph, and that is a very good library for graph operations. So to define graphs and run graph algorithms. And evaluating a synchronous circuit is actually a graph problem. So we have to find a topological order dependent or based on the dependencies in between components, so that we are executing the components in the right order. So that is why we are using petgraph here. And there are some guiding principles how we did this. So we have a clear separation in between synchronous components and those that are just combinatorial. For those of you with digital design background, you're familiar with this, but synchronous things, they are dependent on the clock. And nothing happens unless you give a clock signal to them. While in a combinatorial logic, that means that they can be seen as a function directly from their inputs to their output. And we distinguish in between synchronous or combinatorial components. And then we are able, based on that, to derive a topological order for the simulation. And actually, to compute a new state amounts just to evaluating the components in this topological order. And then regarding the actual visualization or the GUI, we made a clear distinction in between views and models. So the models, they are acting on events, while views are passive and just viewing data. Yeah. It's a flat hierarchy, so that means that the simulator will just show components in one layer. So you don't have subcomponents within components that you might want if you are building real hardware. But for purpose of just simulating or viewing it for the students or for the designers, this is the, at least for now, what we have as the guiding principle. And regarding the layout, how should you visualize the interior of a CPU? Well, you could think of automatic ways of deriving the layout, dependent or from taking the dependencies in between components into account in order to create wires in between them and have them laid out in an easy viewable way. But doing that is a really hard problem. So automatic layout of any kind is difficult, and this type of systems are not easy to lay out automatically. So instead it's grid-based, so you as a designer of a model, when you're building the specific simulator using this tool, you have to give coordinates to each component. So that's more like very high-level design overview. And we wanted it to be modular, so that the SyncRim library just gives the standard components and the execution engine and the GUI, nothing more, and it's up to you to define the models, the actual, if it's going to simulate a RISC-V or a MIPS or something like that. That's completely outside of the simulator itself. And each specific implementation can define its own components for its use. And it should be possible to load new components without recompiling the framework. So there should be no hard dependencies. So once you have made your initial layout and you want to move one component from there to there, you shouldn't need to recompile the framework at all. It should just be able to change the underlying data structure and reload the model. And eventually we would want to have an editor, a graphical editor, so you could actually place the components, drag and drop and so forth. But this is at POC level, so it's a proof of concept so far, so there is no editor. Yeah, and we're demonstrating some features of that. It's in early development. We started, a month back maybe, so I spent the last 3 nights to do some polishing for this presentation, and now I think it should work quite nicely, at least to show the ideas. And we are really interested in having other people involved, so if you are interested in graphics programming and maybe also simulation of hardware and so forth, feel free to contact me. And we can include you in, we can make a Discord group or something like that, and we can work on this together. I think that's it. It's a fun project. So all this basic stuff are working. I don't know what happened here. Seems like a blank line. Yeah, that was the last changes I did from our camper. So I was sitting writing the documentation before coming here, and obviously I slipped on the keyboard. So the idea is that you can forward the clock, meaning that you can send the clock pulse and see what happens, and you can also reverse what already happened, so you can travel in time. So you can see that what is happening in this digital circuit, and then you can go back and what was the cause of a problem, for example. So it's very nice when you later can set breakpoints and stuff like that, that you can rewind the code and see what was causing the problem. And that is quite unusual, that you have the possibility to rewind when you are looking at simulation. It's typically just one way. And you can also reset, so if you want to start the simulation all over. And this part for history, rewind, was something that I did this morning, so I'm not sure that it's completely correct. So what we have already implemented, that is an adder, a generic multiplexer, so it can take any number of inputs. We have constants, we have probes, so that we can inspect the values. And we also have registers or synchronizers. So that is things that already work. And the list of to-dos are much longer, as you see here. So what we want to do, yeah, still it's quite primitive. We can just clock the system. We cannot have it running in continuous mode. Doing so is sort of pointless without having some sort of stop condition. But we would like to have a very generic approach to stop conditions where you can enter an expression or state an expression, and when that is fulfilled, the simulator would stop. And that should go for any signal in the system. And doing so dynamically is a bit of a challenge in Rust, but I think it's doable. Because you would want the programmer or user to be able to add new constraints or new expressions on the fly without recompiling anything. But there are some ways of doing this in Rust. Currently, well, the models, they are exported in JSON format, and these are quite easy to edit, as you will see later when we run some demo. But still, it would be preferable to have some actual editor for this. For simplicity, each signal is now just a U32. So we started out by that. Later, we might want to have bit fields or something like that if we would want to go closer to what the real digital system is doing. But for demonstration, U32 is good enough. So it's a vector of U32s. That's the whole system state, as you would see. There are some bugs or shortcomings. For example, if you have a register connected to another register, connected to another register, and then back again without any combinational logic or combinatorial logic in between, then the order of evaluation is done deterministic. And by that, it will give us the wrong result. So this is something that I know is not implemented yet. And of course, we would like to have more commodity components, like generic instruction data memory components. If we are going to build simulators of real microprocessors, we would want to have memory, of course. And other components like signed zero extend boxes, generic demultiplexers, and yeah, things like that. But my experiments so far has been mostly just to get the sort of framework going, and then one can add more things later. Yeah. So the goal is, of course, that we should be able to emulate the RISC-V that Henry is using in his courses, and the MIPS or RISC that we are using at LTU. But as I mentioned, it is a general simulator, so you can actually simulate whatever in it. It's just up to you who or what you want to do with it. Logging, of course, this is just an implementation thing, but when you are debugging a framework, it's important to have logging so you can actually see what's happening under the hood. So it's more of an implementation issue, but the VCF framework has no logging framework itself, or it's not using one of the Rust logging frameworks, so therefore I didn't do any smart logging, so it's just println debugging for now. There is no error handling, so if something goes wrong, you will just panic. But in the future, we want to have something, if students are going to play around with this, then it needs to be a bit more like your CLAP thingies that have nice error handling. Yeah, and of course, if this is going to be real development in the future, then we need to have a CI and unit testing, integration testing, and all this, of course. But it's not done. So there are many things to do, but there are some things already done. And let's see what we can do here. We can run an example here. And it looks like this. So it generates a background, a grid, and then we have a few components, a constant 4 up to the left, a register symbol below, and that means that its input value will be propagated to its output when you press this clock button. And then you have an adder, which is nice and red. I don't know why I choose these colors, but and then some sort of teal colored output. So it's just a probe. So this 4 over here is a probe. So what's happening here? We are in reset now, meaning that we haven't clocked the system yet. And that means that the register here up here is producing a 0, and we are adding 0 plus 4, and the output is 4. And now let's see what happens if we press the clock button over here. Then it changed to an 8 because we had a 4 in here that propagated to the output. So now we are adding 4 plus 4 and coming to 8. And guess what happens if we press clock again? What should we get? 12. Yes, we got 12. So something is working. And we can also regret pressing the clock button by the unclock button, and we get back our 8 or our 4. But nothing happens if we try to rewind further. If we clock it and then press reset, we're back to the beginning, like that. So I think that it's mostly doing what we expect it to do at this point. For debugging reason, I also draw the raw state. And in this case, the raw state is 4 signals. One is for the constant, one is for the register output, and one is for the register input. Because the adder itself is just referring to the constant, referring to the register. And the register here is just referring to the output of the adder. So that are the 4 or the 3 different U32s that are involved here. So what is happening when we are, now we can rerun this by just running cargo run here. And now it was blistering fast. So it just loaded the JSON file for this. So starting up the simulator once you have compiled it once is super fast. So it allows us to do changes. And if we take this, close it down, and go to files over here, we can see, oh, now I pressed on the wrong button here. We have a model JSON over here, and it's packed, so we have to use formatting. And this is what we have in the JSON file. So the first thing is our adder. The type here is because it is defined by the add struct inside of the simulator. And it has a unique ID, add1, and it has a grid position 200, 120. So the first parameter is the X, and the second is the Y. And then we have, for this adder, we have 2 inputs that is connected to the C1 component with the output 0 of the C1. And from the register, it's the register R1, the output number 0. And all of these components have just one output, so obviously it's the first output, which is index 0. So what do we have more? Yeah, we have a constant. It has just a position, an ID, and a value. And we have the register, and it just has the position. It has an input telling that it depends on the output from the add one here. And then we have some wires. And these are just coordinates for the size of the wire. X, in this case, starts from 220, 120. X is, or the first parameter is the size in the length in the X direction. And another wire, and another wire, and another wire, and another wire. And then our probe for showing the result, that is also looking at the result of the adder. So, pretty straightforward. It's easy to understand how this relates to this graphical model. And if we want to change this constant to 8, now we are changing the model. Then we can go back and rerun the simulator without changing, recompiling the framework. So it just loads the model and runs it. And when talking to these guys at the Discord channel for VCA, they were really enthusiastic that somebody was doing this type of things with VCA, because it was not designed for this, because it's something that is not usually done for graphical user interfaces that can dynamically load new models into them. So in this case, we see that we changed the constant to an 8, and now the addition of 0 plus 8 is 8, and so forth, and the raw state is 880, and we can run this, clocking it. And I have just one more short demo here. That is, if we go down to the MIPS subfolder and cargo run example MIPS, then we have essentially the same structure with the adder, but now we are using this to generate an address to the instruction memory. And the instruction memory then responds to the output here with the value or the data stored at address 0 in this case. So we can play around with this and clock it. We see that nothing works. No, I was not hitting the right button. Now it's address 4 because we added 4, and that's typical for 32-bit architecture, that we have 4 bytes in each instruction. That means that the next instruction will be at the offset of 4. And now we got the 1 out. That is just telling that it was the first index. Earlier on it was the index number 0, number 1, and we can clock it and get output like this. And we can also go in and alter the model. And we have a subfolder here where we have the MIPS. We can see how it's constructed. We see this is the code for generating the model, and it's quite similar to the JSON, meaning that we are creating a component with the name add here, or the name of the struct is add. It has fields, ID, position, input, and so forth. A bit more detailed, but essentially the same thing. And here we can see that we have the program memory, or the instruction memory, and at address 0, we put the value 0. At address 4, we put the value 1. At address 2, or 8, we put the 2, and so forth. That was exactly what we saw in the simulation we run. And if we go to the MIPS JSON, we can open that up. And we can change the contents, for example, of the data memory, or sorry, of the instruction memory. Let's say we start with 100, 10, 120. Here we have an instruction which is encoded as 299. So this would be the binary representation of the instructions if this was a real simulation of a processor. And now we have saved this JSON file, and we should be able to just make cargo run. And we should clock this. it did not work. Maybe I put the, yeah. Why did it work, not work? I think it works if I run it from within if I run it from here, let's see. We should run just main. We can look at how if you're just running the simulator, what it does is that it looks up a JSON file and then puts that into a component store and then kicks off the GUI, which starts up the simulator and everything. So we should be able to run it by just pressing here the first time around. Well, it will recompile everything. But after that, I think it should be fine.
I guess you have two mixed dots.
Yeah, I was editing. Because it created this.
Oh, yeah.
Yeah. Oh, maybe it does not. Perhaps it's blocking. Let's see. Or maybe I killed it. Let's see. Yeah. Now we see that the changes that we made, like this 110 for the first instruction, clock here 120, and then we should have our 299 famous instruction. So that's about it. If you're interested, I can show you more about the implementation behind. It's not using any crazy code. So there is no, I mean, at least the usage of this VCA together with implementing this simulator requires no unsafe code at all. There is nothing strange going on here. I can run it on the stable compiler, so there is no dependencies or crazy features that might be dropped later. So it should be fairly future-proof, unless the VCA guys decides to change things around. But it's approaching release of the VCA framework. They've been working hard with documentation and so forth. Any questions? Should we use the microphone, or you just speak loudly? And
no, just yell so loud.
Yeah.
We should use the microphone. The one on the table is okay.
I have no idea how to operate this.
Yes. So
this button, and now I think we have audio.
EP. How does the unclocking system work? Do you have like just a history stack of previous states, or does it actually run the simulation backwards?
It's just a history stack.
Okay.
Yeah, so it's a very simple way of doing it.
Okay.
Yeah.
And then you mentioned Visio uses CSS. So is it like WebView based sort of thing? Does it have like a browser engine? Or
no, not okay. You don't need that, at least. But I think it's just used this CSS format for the styling. So I don't think that it's rooted in web in any other way than the syntactic way of describing these themes. So we could ask, of course, the main developer, Geometric, is usually online on Discord. So we could ask him, you can forward the question to him.
You mentioned that the components would be dynamically loadable, like you can change the, but that's not implemented yet, right?
It is.
I mean, the behavior of what add does is like just an
no, not the behavior, not, but the layout is. So it's just that you have, if you want to change how the multiplexer is implemented, then you need to recompile
right,
it.
If you would add a component, if you add like a totally new component, then you also have to like add the implementation for that, right? Like describe the behavior. Let's say I want a NOR port or whatever. Maybe this is a silly example.
You can put them in the library and just use them. I can just show you how the extension looks like. So the only thing that this MIPS model is doing is adding a single component, this inster mem component, and then it relies on the library components that were already given in the standard SyncRim.
Okay, so the framework is meant to be like a crate on its own, and then you link your application together, and then you add special features you want.
It's even like that the library system is such that, for example, if you're going to implement a risk architecture, then you should be able to make all the components that are common to all risks into a library of its own. And then if you are doing an ESP32C3, then you just add the ones that are specific to that, and you reuse the ones that comes from the MIPS crate or from the RISC-V crate, and then you have the basic ones that comes from the framework itself. So it's very modular in that way. And that was the challenging part, actually, to make the simulator to not know about what kind of components the user is going to implement. So we don't need to change the framework in order to add new components. There might be cases, since I haven't done any real designs with this yet, where we come to the conclusion that the traits that we have defined, the commonalities in between all components, is too weak. And then, of course, there will be a breaking change. But so we need to experiment a bit more until we sort of finalize this.
More questions? Mm-hmm.
So if I understand correctly, you are basically developing your own HDL of some sort. So is it possible to reuse some existing HDLs?
In SyncRim, the Java implementation, then we made a proxy to Cadence HDL simulator. But we lost the license because they were bought by Mentor or something like that. They changed something, so we didn't pursue that path. But it's, this one does not implement it, but why not? I mean, it's just if you want to implement your a subsystem or a component in real HDL, as long as there is a simulator that has the ability to communicate over some port, so that you can set the inputs, simulate, and get the outputs, then it should be possible to visualize using VCA and this framework. We did it for Java, I can tell.
But for example, if we have a CPU implemented in some common HDL format, then it should be possible to basically load some sort of a VCD file with the general waveform and then visualize. Is it kind of
but we never did that, because the point of this is that you should be able to I mean, maybe this is a good solution to use the output from the whole. I mean, what we did was more or less an online simulation, meaning that we were communicating with the simulator and putting data into the simulator and getting data out of the simulator in order to just visualize it using this API. But what you're saying is a bit different. It's more static, that you should just be able to replay a simulation in this as a visualization. Is that correctly understood?
Yes. I just don't quite understand the whole idea of this online simulation. I mean, it's supposed to support some sort of on-the-fly modification of the values, for example?
Yeah, I mean, this is one thing that when we are teaching the computer engineering course, they are reloading they are altering the assembly and using off-the-shelf tools to compile it to a binary. And this instruction memory component that we wrote in Java is just taking the obj dump and loading that, and you should be able to continue. But I think that could be compatible to your idea that you just get a VST out or something, a simulation waveform out, and parse that. It's just that it was more straightforward and easy to implement the components directly in Rust than, at least for this type of playing around with the framework ideas. But for sure, it is a possibility to integrate with waveforms.